morning, everybody. Today we are going to finish talking about the method of sections before we get started on Chapter 1. So we are following along from the homework, from the handout that we had, beginning with section 6.8, analysis of plane trusses by the method of sections. All right, now when you look at a section when you look at a truss like this, which I shall attempt to draw and then do the analysis over here. We already, from our method of joints analysis, we know some stuff about this. Let's see, first of all, how many triangles do I have? 4. So, I've just totally messed it up already. Good thing I want more paper. We already know stuff. We know that each one of those structural members is in tension or compression or in zero stress. And we know that we can do the analysis of the tension or compression in each of these structural members based on, first of all, doing a good free body diagram of the entire structure, and then second of all, looking at each joint or each connection where the structural members go into each other in order to figure out whether the structural member in question is in tension or compression. So what we have here, we have some geometry. We know that this is 4 feet tall. And we know that it looks like each one of these is to the center 3 feet. So each one of those spans is 3 feet, or the entire span from here to here would be 6 feet. So we know a little bit about the triangles. We also know, I'm going to use a different color pen today, that we have an applied 15 kilopound or 15,000 pound load here. And at point B and C and D, we have applied loads. This is 10 kips, 20 kips, and 30 kips. All right. Now, in the past, sometimes we've had symmetry of loading as well as symmetry of geometry. And in those cases, we could shortcut our free body diagram. But here, our truss is geometrically very symmetrical, but the loading is asymmetrical. So we're going to have to go through the whole process to get our reactions. Now, the one thing that we can see is that A, as a fixed support, will bear an x directional force and a y directional force, but E, as a rolling support, will only bear a force in the y direction. So after we do that, what they ask us for, I'm going to have to label a few more points here on my truss. This is A, B, C, D, E, and then up here we have F, G, H, and I. And the authors have cut the truss right here with a line AA prime, or they just call it AA, or call it AA prime. And what we're going to get at is we want to know the tension or compression here, here, and here. Well, from doing method of section or method of joints, we could chase that all the way back. But method of sections is actually a shortcut to get us right to the guts of this, so that we don't have to find out what the tension is in AF and FG and so forth. We can just go straight to here, okay, and do it like that. But in either case, method of sections, method of joints, the first thing is we have to do a free body diagram. Summation forces X equals 0. So we only have one. I'm going to draw it because I know it looks like this, the reaction at A in the X direction. This would be the reaction at A in the Y direction. And here we have the reaction at E in the Y direction. So in the X direction, all I have is a 15 kip applied force. And the way I have it drawn, RAX negative equals 0. So I know that RAX is equal to 15 kips. Okay, now in the Y direction, we have a couple more forces. We have a reaction at A in the Y direction, which is unknown and drawn positively. We have minus 10 kips, minus 20 kips, minus 30 kips, and then we have plus RE in the Y direction, and those things sum together equal 0. So if I add these together, I get negative 60 here, bring it over to the other side, I get a positive 60 kip, RAY plus REY equals 60 kips. Okay, I have one equation, two unknowns, can't solve it. That means I must do a summation of moments. Right. Now, I would like to eliminate as many forces as possible. I would specifically like to eliminate either RAY or REY because those are my two unknowns. So I'm going to take a moment here about point A. And I know that the summation of moments about point A on this entire truss is going to equal 0. So that makes RAX and RAY do not produce any moments because there's no moment arm. So I have a 10 kip force vertical acting 6 feet horizontally from point A. If I visualize putting a push pin here, that will spin it clockwise, so that's negative. Similarly, I have a 20 kip force acting 12 feet away. Once again, clockwise, so it's negative. 30 kips times 18 feet, also clockwise. And now I have REY, which if I put a pin here and the way I have it drawn, that's going to be counterclockwise, so it's positive. REY times this entire distance, which is 24 feet. And then I also have this 15 kip pound, or this 15 kip force. Now the 15 kip force is horizontal, so that means I'm looking at the vertical moment arm, which is 4 feet, because once again it's that perpendicular right-hand rule thing. And if I put a pin here and I pull on this, it's going to be clockwise, negative once again, and those things sum together equal 0. The good news is I have one unknown, which is my REY. All right. So this is 60 kilopound feet, negative. This is 20 times 12 is 240, negative. 30 times 18, I believe, is 460. Anybody's welcome to check my math. Like I've told you before, if it's not correct, I'm not teasing you. It's just me making a mistake. And then 15 times 4 in the negative sense is 60. And those things added together equal 0. So to solve for REY, I add these together. That's 300, 760, 820, all of which are negative, so they become positive on the right-hand side of the equation. That equals REY times 24. So if I divide both sides by 24, I get a value of 820 divided by 24.
I have a question.
Yes, sir?
Between the 30 kp, 18 feet, and the 20, is that a minus sign in between them?
Here?
Yeah, that one, the one there. It's
Yes. Yes, because they're all clockwise moments. Absolutely. Yep. All right, so 820 divided by 24 equals 34 and a 0.1667. So I'm just going to say REY is equal to 34.2 kips. All right. Well, if REY is equal to 34.2 kips, that means RAY plus 34.2 kips equals 60 kips, or RAY is equal to 60 minus 34.2, which is 25.8. And I've drawn the signs correctly. Okay, so now I have a value for RAY, a value for RAX, and a value for REY, so I've solved my truss. Okay, now what if I want to know what is GH? And I don't want to just chase the whole truss. This is where the method of sections comes in. The way that the method of sections work is in the same way that the summation of forces X, summation forces Y, and the summation of moments, everywhere on this truss, on every single joint, has to be equal to, have to sum to 0 in order to maintain static equilibrium. If I just take a chunk of this truss, everything has to sum to 0 as well. And so that's the analysis process. So in other words, I can just look at this part of the truss, or I can just look at this part of the truss, and everything has to sum to 0. Anything that I cut becomes a force. Yes?
So in order to solve for sections, do you have to find all the external forces on the joints first?
You have to at least find all the external forces on one side of where you're cutting.
Okay.
Yes, that's a really good point. If you have a way, like, let's just say, here I couldn't do it, but if, because I have those two on either side, but if I was able to find RAY and I didn't know what RAY is, it wouldn't matter. I could just cut and use that side. So everything else on the side that you cut and that you're not using is taken up in the tension and compression of the members that you've cut. That's kind of the beauty of this whole thing. All right, so I'm just going to cut this way, and I'm going to draw, or attempt to draw. This is where my artistic prowess fails me, so I kind of have to copy it sometimes. And you may not be able to see that, but I can kind of see where I am. So I have GH here, and I have, that would be GC here. And I've cut both of those. And I have also cut, what is it, BC. All right. Then the rest of the truss just looks like this. Okay? I don't have to analyze anything there, but I do have to pick up the external forces on that side of the truss only. So here at point B, I have a 10 kip force. And then, of course, I don't have any other forces on the truss except for the reaction at A in the X direction and the reaction at A in the Y direction. Okay? And from my analysis, I have found that this value is 15 kips. It's pointing to the left, so I could write it as 15 kips to the left or negative 15 kips. RAY we found to be 25.8 kips. Okay, so what the method of section, the shortcut part is, I can then view this, this, and this as forces. So I just have 6 forces, and I do not have to worry about the internal tensions or compressions. But I do have to decide which way things are going to be pointing, and I may not be able to choose, I may not be able to isolate whether this is pointing to left or right, left or right, left or right. And in that case, I try to choose things in a positive sense. So I'm going to choose GH to look like this. And then BC, which is also horizontal, could either be to the right or to the left. I'm just arbitrarily choosing it this way. And then I have a positive and a negative. This is larger, so I have more stuff going down than I do, or more stuff going up than I do going down. So this one is almost assuredly going to look like this. In other words, the component, this has both an X and a Y component, and therefore it has to be pointing down. Now, I have 3 unknowns, GH, GC, and BC, and that indicates that I will probably need 3 equations. So the other piece of good news with the method of sections is we do get to use the moment equation because we now have a shape. So we could take moments about a point and find out moments as well. But I can only analyze with 3 unknowns. Otherwise, I would have to cut somewhere else. Okay, one other point before I do this. If you look at this line that I've cut, and I would just refer to this as a cutaway, I've drawn it straight. That's pretty arbitrary. The only thing is it has to cut through the entire truss. You have to be able to split the truss into 2 pieces, and everything that's cut becomes a force in your section diagram. All right, so let's take a look here.
So you can cut it any way you want.
Yes, you could cut it any way. Whatever structural member you want to get the tension or compression in, you cut that one, and then you cut whatever else you have to cut in order to have a section that separates like this.
I'm just going to do like an A to A GH through point C.
Oh, well, it's not really going to matter. I mean, it seems like it would, but if you go through point C, you just want to make sure that you don't, you're either going to do either one side of point C or the other. But yes, you could do it that way if you wanted to, so that you wouldn't be cutting BC, that you would be cutting CD instead. But if you did that, You'd have to swing it over this way so that your unknowns would be this, this, and this.
Do they have to be angled? It can't be like a straight.
It can't, well, what I'm saying is if you cut right through C, what does that mean?
Yeah.
I mean, in other words, this force has to either be on the truss or not on the truss. So, and if you cut right through it, you don't really know.
Yeah.
All right, yeah, good question though. All right. So, let's go ahead and take a look at what we got then. All right, so first of all, and I'm sorry, I want to put a piece of gray paper underneath this because sometimes it leaves little dots on the platform. There, that's better. Okay, summation forces X on this section equals 0. What do we have? Negative 15 kips. We have the entirety of BC, which I've drawn positive. We have the entirety of G sub H. And we have the component of G sub C, which is positive as well in the X direction, plus G sub C in the X direction. We'll have to use a little trig to figure out what that is. That equals 0. In the Y direction, we have RAY, which is positive 25.8 kips. We have this applied load at B, which is negative 10 kips. I guess I should just do that. Okay, this and this do not have any X component, but G sub C, excuse me, any Y component, but G sub C does, and it's negative. So here I have negative G sub C in the Y direction equals 0. All right, now I can also do a moment equation, which I'll do in a moment, But anyway, if you look at this equation, we only have one unknown. So we could just go right to our Y equation and solve for G sub C and get one of our numbers out of the way. All right, so we need to know a little bit about the geometry of G sub C. The trig, really, sorry. So G sub C. We know that the height from the picture of this structure is 4 feet. Oh, you can't. How's that? There you go. That should be better. And I actually can't see it either because I've got it covered up by my calculator. Okay, so from G sub C is 4 feet. And from the center of the truss to point C, this entire span is 6 feet. And we're told specifically that that's 3 feet. So we have a 3, 4, 5 triangle, don't we? Okay. Because if it's a right angle, it's a 3, 4, 5. So we can do trig. We can find out what this angle is because it would be the inverse tangent of 4 over 3 or something like that. Or we can just recognize that, that the Y component is going to be 4 over 5, right? In other words, the opposite over the hypotenuse or the cosine of that angle. So here I could just write 25.8 minus 10. Do we see it? Yes, we do, kind of. There we go. Minus G sub C times 4 over 5 equals 0. And using this math sentence, I can solve for G sub C. G sub C over here is equal to 25.8 minus 10, which is 15.8. And then I have to multiply by the reciprocal, 5 over 4. And I get that the value of G sub C is equal to 15.8 times 5/4, which is 19.75 kips. All right. All right, now the other thing is, when we write our little answer block, we have G sub C equals 19.75 kips, and it is pulling on the joint, isn't it? So is G sub C in tension or compression? Very good. It's in tension. All right, so do you see, first of all, if all we had needed was G sub C, if that was the only thing they asked, do you see how much easier the method of sections is? In other words, we had to chase everything all the way through. All right. Now, G sub H and B sub C are going to be also relatively easy. When I look at this truss, if I were to take moments about this point, which is point A, these two forces have no moment arm, and B sub C is collinear, so all it does is pull. It doesn't make a moment at all. So if I take my moments about point A, set it equal to 0, I will not get a moment from this force, or B sub C. And what that's going to do is allow me to, we're going to have to do one more thing that we haven't really talked about in here, but that's okay. I'll show you in just a moment. We will have only G sub H as an unknown, and we'll be able to solve that. All right, so let's do that. This don't make any. The 10 kilopound force creates a clockwise or negative moment and has a moment arm of 6 feet. B sub C does not create a moment. All it does is pull. All right. And G sub H, the way I have it drawn, will also create a clockwise moment, which is negative. It's horizontal, so the moment arm is the vertical 4 feet. But then we have G sub C, which we know the value of. But the confounding factor about G sub C, the thing we haven't addressed, is G sub C is neither horizontal nor perpendicular. So what's the moment arm? Okay. Now, this is an easily answerable question. It's not a mystery. So we'll just show you how. I'll show you how to do it. But there's two ways that you can do this. You can either get the perpendicular distance to this point from the force. So in other words, I haven't drawn that terribly. It would be more like that. You can get this distance, or you can break G sub C into X and Y. And that's what I would do, because we've already got almost all of that work done. So G sub H. Okay, so then let's do this. So we have, if we look at G sub C, we have an X directional component. So we can say, and that's going to create a clockwise. So G sub C in the X direction times, since that's X, the vertical moment arm, which is 4 feet. But then in the vertical direction, the G sub C in the Y direction, we want the horizontal moment arm. And G sub C in the Y direction is 3 feet plus 6 feet, which is 9 feet, because this distance is 3 feet, 3 feet, and 3 feet. So it's 9 vertical or 9 horizontal feet from that. And the way I have it drawn, that is going to be clockwise as well. All of these are clockwise moments the way I have it drawn. Okay, so I think I probably have something wrong, but we're going to find out. I mean, in terms of my directions. My equation is functional, but in terms of the working of it, we're going to have to figure that out. Okay, we know the value of G sub C, don't we? 19.75 pounds. So let's go ahead and do our work here. Let me get another piece of white paper. Ugh, you're not white. You're gray. Here we go. So I'm just going to write that moment equation out in a single line. So we get negative 10 times 6 is negative 60. And we have G sub H, which is our unknown, times 4 feet. Then we have G sub C in the X direction, which we know the entire value of G sub C is 19.75. And going back to our triangle in the X direction, 3 over 5, right? 3 parts of 5, or 3 over 5, times that moment arm, which is 4 feet. And last but not least, G sub C in the Y direction, which we already found the value, but that's okay. We'll just do it this way. minus the same 19.75, only this time it's the force in the y direction, so that's 4 over 5 for my triangle, times that moment arm, which is 9 feet, and those things added together equals 0. So what's the good news? Well, I look at this, and the only unknown I have is g sub h. So if I do my math, I get minus 60. I'm going to take this term over to the other side just to eliminate it over here, and it becomes a positive. G sub h times 4. So this is 60. I have minus, I'll go ahead and do a calculator, because if I do it in my head, I'll mess it up. So I have, first, 19.75. Times 3 over 5 times the moment arm, which is 4. So this value is 47.4 minus, now this is 9 feet, yes, so 19.75 times 4 over 5 times that distance of 9 feet is 142.2 equals that. So if I take 142, it's a negative, of course. 47.4 is also negative. And 60 is also negative. I get a value of 249.6 in the negative sense, negative 249.6. And if I divide both sides by 4, I get the value of g sub h, which is 62.4 equals g sub h. All of my loads were in kips. All my distances were in feet.
That's not negative, right?
It's negative. Yeah, what does that mean? Do you know what that means? It means I chose it backward, right? So that means that g sub h looks like this. Okay? G sub h then has a value of 62.4 kips, but it is pushing on the joint, not pulling on the joint, so it's in compression. Okay? Now the last thing that we cut was B sub C, so we can find B sub C from the summation forces X equation, because we know G sub H and we know G sub C. So to finish our analysis, we get negative 15 plus B sub C plus G sub H, which we found is actually going the other way, so that's a negative 62.4, plus G sub C in the X direction. In the X direction, G sub C is positive 19.75 is the entire amount. But in the X direction, we are at 3 parts of 5 equals 0. And we can solve for B sub C. So if we take B sub C equals, those two added together become positive over here, 77.4 plus, oh, this is going to be negative, sorry, minus 19.75 times 3/5. That value is 11.85. So if I take 11.85 and subtract it from 77.4, I get a value of, that wrong, 77.4 minus 11.85 equals 65. B sub C equals 65.55 kips. B sub C equals 65.55 kips. And it was drawn correctly. It's pulling on the joint, so it's in tension. Okay.
So you can use the force that, like on G.
Yes.
We can use that because we found it in the Y.
Right.
We can use that on the X as long as we do the
That is correct. You're looking for, you found the y component, and if you know that angle or you know the lengths of the sides, you'll be able to find the x component as well. Very good. All right. So do you guys have any questions? Pretty much fun, huh? All right. There's a lot of analysis in this, so I ask you to spend some time in it. If we go back and we take a look at the page, we have submit homework number 1. It says Friday, September 7th. I'm going to change that to Monday, September 10th. And it will be due Monday by the end of the day at 11:55 p.m.
So we could like work on during the weekend and then scan it and send it to you.
That would be super. That would be absolutely super. So, all right. And you have the homework template. So you know how I like to have things turned in. And I do. Yeah, I know. This is serious engineering. This is like, I tell people, this is like the equivalent in an English class of 1-inch margins, double spacing, APA format, or whatever your teacher wants you to do. So this is just, it lends to your credibility as an engineer when you do things in this format. Not to suggest that brilliant work could not be done on a cocktail napkin with a crayon, but this is what we like to see. All right? All right, so no questions? All righty, so I'm going to stop streaming, get started on the homework. I will change the due date, and I will see you Friday for starting with Chapter 1. And actually, after you learn how to do the tension and compression in structural members like this, you will see that you have developed a lot of skills, and that Chapter 1 will actually be a lot easier. I mean, it's not easier like I could have started with it and been easier.